The illusion of precision, applying measurement uncertainty to ship inclining experiments. This is a short talk on engineering judgment. I am Bijimon Punnoose, CEO of FloatSys. One of my professors had a habit that puzzled many of us. Whenever a student presented a calculation full of decimal places, he would smile and ask, "Do you really believe all those decimal places?" Engineering calculations are deterministic. Run the same number twice, you get the same answer. That's not the case with measurements. A calculator has no idea how accurately its inputs were measured. It simply does arithmetic on whatever numbers it's handed. So when a result displays 6 or 8 decimal places, those extra digits are an illusion of precision, not additional knowledge. An engineering result should never claim more confidence than its measurements can support. Take a digital inclinometer that displays heel angle to a thousandth of a degree. That's its resolution, the smallest step it can show. But wind, vessel motion, mooring restraint, and instrument drift, etc., limit what you can actually trust to about 200ths of a degree. That is 20 times worse than the display suggests. Resolution is what the instrument can show. Uncertainty is what the engineer can honestly claim. A few terms worth pinning down. Accuracy is how close a measurement is to the true value. Precision is how closely repeated measurements agree with each other. Resolution is the smallest change an instrument can display. Repeatability is the consistency under identical conditions. And measurement uncertainty is a quantified estimate of the doubt in the result. These are related ideas, but they are not interchangeable. And mixing them up is where the illusion creeps in. Unlike draft or heel angle, a ship's metacentric height, GM, is never read directly of an instrument. It's calculated from four independently measured quantities: vessel displacement, the shifted weight, the shift distance, and the measured heel angle. Every one of those carries its own uncertainty, and every one of those uncertainties propagates straight into the final GM value. So, where does that uncertainty actually concentrate? In most inclining experiments, heel angle measurement turns out to be one of the largest contributors, not the draft readings most engineers instinctively focus on. And that matters because overall quality of GM is controlled by whichever source dominates the budget, not by ones that happen to be easiest to refine. Okay, let's put real numbers on it. On a Suezmax tanker, a realistic 10 millimeter draft uncertainty on a 4,000 square meter water plane works out to roughly 40 tons of displacement uncertainty. A 1,000 ton ballast transfer, known to 2% already, carries 20 tons of uncertainty in the healing moment. Meanwhile, a portable equipment, a ladder, a toolbox, gets weight to the kilogram. Against tens of tons of draft and ballast uncertainty, the difference between 18 kilogram ladder and a 22 kilogram one changes absolutely nothing. But don't mistake that for a universal rule. On a Suezmax tanker displacing well over 150,000 tons, 20 kilograms of loose gear is rounding error. Put that same 20 kilograms on a 12-meter fiberglass boat, displacing only a few tons, and it can be a measurable fraction of the total displacement and of the healing weights used in the test itself. There is no universal small enough to ignore. The threshold is set by the vessel you are actually inclining. This is where judgment starts to matter more than mathematical effort. Once draft, ballast, and heel measurements already limit what's achievable, spending hours refining a quantity that's orders of magnitude smaller adds nothing to the result. Good engineering is in measuring everything to the highest possible precision. It's recognizing which measurements actually move the results and concentrating your effort exactly there. That doesn't mean small measurements are always irrelevant. It means every measurement should be weighed by how much it actually affects the result. And this isn't only a naval architecture problem. A strain gauge might display strain to a resolution of 1 microstrain, but temperature drift, gauge factor tolerance, and lead wear resistance often push the real uncertainty to several microstrain or more. Stress is then calculated from that strain through Young's modulus, exactly like GM is calculated from draft, ballast, heel. Resolution is in uncertainty, and a calculated result is never more trustworthy than the measurements behind it in any engineering discipline. So consider two ways of reporting the same inclining experiment. GM equals 2.347891 meters is misleading. It claims a confidence the measurements never had. GM equals 2.35 plus or minus 0.05 meters is honest. It carries less numerical detail and considerably more engineering information. The most experienced engineers are rarely the ones who report the most decimal places. They are the ones who know which decimal place is the last one that can be honestly be defended. Thank you.